Okay, so we good? Yeah. So let's get started. So we discussed the main ideas of the basic model in computer vision, which is based in how the human visual system was believed to work back in the day. And you have, as always, beautiful slides with nice pictures in Canvas. So make sure to check those. But basically, this is your eye, this is your brain, right? Remember? And then there's some processing here in the back of the eye, in the retina. There's some processing in subcortical areas right here, especially the LGN. And then this is projected to V1 and V2 and so on. And then this will go through the ventral pathway toward the temporal lobe, different areas of temporal cortex, where different types of processing occur. And this first portion here we call low-level vision. Right? So we're interested in two things. So, okay, before I get to this, so extremely important to understand, I mean, this is super important to understand. Everything that we're discussing now, it's based on this antiquated model of how the human visual system works, right? That's not how the human visual system really works, but there are components of that are still believed to hold. So because computer vision is such a modern research area, it's just been stuck for now into this model, right? So within this model, then we have two questions to address. The first one, which is the one we're trying to address right now, is what are these processes in these low-level vision areas, right? What does low-level vision system really do, or does? So what does it do, really? So let's think about this. The very first thing that we discussed was Hubble and Wiesel's work, where they put electrodes in the early visual cortex or subcortical regions of the cat, and they discover that when you have edges, right, of light, so light, no light, or vice versa, then certain neurons spike, right? Indicating, supposedly, that when you observe a change in intensity, there is a spike in your brain or in your cells. And that led to the hypothesis that early visual cortex or low-level vision is involved in detecting edges and other features in the image that are relevant to then achieve higher level tasks such as object recognition, right? So in the last lecture, in our second lecture, we saw how you can actually use this this idea to design edge detectors, right? So we have seen how to define, say, edge detection, right? And we talked about this in 5460, didn't we? We spent a lot of time defining linear filters and Fourier analysis and all the different kernels that you can use in linear filters to detect edges. We extended this in lecture 2 in our last lecture, right? Where we actually talk about a variety of Gaussian-based filters, Gabor filters, there are wavelets, and then we spent some time with one specific, very famous edge detector, right? The Canny edge detector, which uses the same ideas that we had discussed before, but it has a certain number of additional criteria that are used to make sure that the edges that you get are as good as possible, right? Now, we'll get back to this later in the course, but remember that one of the problems that we have already mentioned about all these edge detectors, not only Canny, but all these edge detectors, is that what's an edge, right? And that's a fundamental question. And this seems such an innocent, simple question, doesn't it? What's an edge? An edge is an edge, right? But when you really look at the pixels in the image, there are edges everywhere because intensity changes almost from every pixel to every other pixel. So what gives, right? At which point do we define that this is an edge or it's not an edge, right? And the way Kenny did that is by defining these three criteria, right? To determine based on some parameters on these criteria what an edge is and what an edge and what is not an edge, right? But understand that that's given by the criteria that you specify in your algorithm, right? There's no easy answer to what's an edge or what's not an edge. And in particular, what you want to do is in your particular application, right? When you go out in the real world and you work for a company and you are implementing a computer vision system for that company, what you want to implement is an algorithm that solves a specific problem. And that specific problem has its own definition, right? Remember what I said in the first lecture? The very first thing, not in computer vision, in all of science, right, is to define the problem. So that's why it's important, right? You define what your problem is, and that will determine what type of edges you need to detect or what your edges are, what are the important edges or features that you need to detect in the image. Okay? So far, so good. Any questions? All right. Note that Kenny edge detector is not the only one. There are hundreds of them that have been defined, hundreds of them that have implementations in either OpenCV or in MATLAB or in any other application that you may be using, a computer programming tool that you're using. So make sure that you check this. I posted a few papers in Canvas that you can look into, right? I have posted in the slides, you have different types of edge detection results with different types of algorithms and the different edges that it gives you, etc. So that's edge detection. Another thing that you can do is to extract other type of features, right? Because edges are just very simplistic features from the image that we can obtain, right? But they're obviously not the sole type of elements, low-level or very basic features from the image that one can extract are there. There are other things that we can extract. In general, we're going to call them unions, for example, as another set. And one particular type of unions that I want to spend some time on are corners. So corners are the places where two edges that we might have detected with an edge detector intersect, right? Or actually end, right? So they have to end in the same location, right? That's a corner. And to remember in this classical model of computer vision, right? In this classical model of computer vision, it is important to go from simpler features to more complex features to some type of representation that is then useful for object recognition, right? And other high-level tasks that we'll get to. So it makes sense, or it made sense back in the day, that once you had detected edges, you would detect structures that were more complex than simple edges, such as corners, right? And that also followed the idea of Hubble, or the studies of Hubble and 𝗜희𝘀𝘁𝗁, that showed that after these very basic cells that I described that were sensitive to changes in light, right, you had other cells that detected whether a group of cells actually changed or spiked because they were detecting an edge, and so on and so forth. So the idea was that you have some cells here represented as circles or nodes of a graph that look at the image, right? So you have an image here, and then you have these neurons or cells, right, looking at different regions of that image that may detect just very simple edges And then here you have some other cells that look into these previous ones that extract more complex features, maybe such as corners, right? And then other types of cells that organize this in some type of a structure, in some type of space that we have to still define, right? And that allows you to do recognition, right? So it's a basic model that we're trying to build. So let's see what type of structures, such as corners, we can detect. Okay. We're going to use the same methods that we use to define edges. We're going to use the methods that we have already seen, that we saw, in fact, in 5460 for linear filters. Okay. And I want to make clear that I'm just going to talk about corners here, but as I'll mention later, there are many other types of features, image features, that one can extract with this same method. And remember that I'm always going to make a distinction between what is a vision problem, right, such as low-level vision, or edge detection, or corner or union detection, versus what are the methods that we use to solve that problem or to address that problem, right? Okay. All right. So how are we going to detect corners? What's the very first thing that we need to do? Well, we need to agree on what a corner is, right? So we need to provide a formal definition, right, or a more formal definition. Okay. So we're going to define corners as the points where, one, there is a high gradient, right? That's number one. And two, within a small window, or neighborhood, if you prefer, right, the gradient orientation changes sharply. So you can say sharp change of the gradient within a small window, or neighborhood if you prefer. Okay. Now, why do we want the first one? Well, high gradient, remember, is important to detect edges, right? Correct? And the sharp change of the gradient within a small window, like this window right here that I have indicated, means that there is a change, a sudden change of the directionality of that edge, right? So how can we mathematically formulate that? So formally, we can detect this as follows. So formally, I can write this as, say, the value h of the gradient of the image times the gradient of the image. And I'm going to sum this over a window, and that's the window that I'm searching within my image, right? This classical window we've been talking about in linear filters that's going to allow us to detect that change. Okay? So this measures the similarity. Remember from 5460 that an inner product is a measure of similarity, right? Because a Hilbert space is defined by a metric given by an inner product, in our case this one. And it measures the similarity between the gradient points. Okay, and we can, to implement this, we can approximate this h using the following matrix, as we have done before in linear filters. We're going to use a matrix. We're going to use the Gaussian as usual. We're going to use the first derivative with respect to x, convolution with the image, convolve with the image, times the partial derivative of the Gaussian with respect to x convolved with the image. And we're going to have here the other element in the diagonal, the partial derivative of the Gaussian with respect to y convolved with the image times the same thing. Oops, sorry, I. And now in the off diagonals, right? So that's going to allow me to detect edges in the x direction and the y direction, right? And now I want to, in order to detect the corners, right, as we have defined them here, I need to detect the change, right? So it's a partial derivative with respect to x and y, or y and x, right? So I'm going to have here, say, this is the partial derivative with respect to y convolved with I, and the partial derivative with respect to x convolved with I. And then here, with respect to, whoops, this is sigma with respect to x, and the partial derivative of the Gaussian with respect to y, and convolve with y, right? Okay. So far, so good. Now, what do we want to find? We want to find points where this is maximized, right? And I'll review this probably later in this lecture. But if, yeah, I think we'll have time to do it today, if not next time. But there is a method that we spend a huge amount of time in 5460, right? That allows us to detect these maximums. Anyone remembers what it's called? Anyone? Really? I'm patient. I can wait. No one wants to collaborate today. Come on, what's the method? Just say the method, right? Thank you. Linear least squares, yes. So we can find the maximums and the minimums, right, with linear least squares. In fact, I can do an eigenvalue decomposition of this matrix and find the corresponding eigenvalues, right? Now, if the image were, or all the pixels in the image were of the exact same value, right? Imagine a grayscale image for simplicity. If they're all of the same value, what would be the eigenvalues of that matrix? Yeah, speak up. There be all what? 0, yes. Why?
Because there is no gradient.
Right? Because there's no gradient. So there's not going to be a maximum or a minimum. They're all going to be the same, right? There's just not going to be any change. So all the eigenvalues are going to be 0. Now, if the window that I'm looking into, right, because I apply this to every window as we do in linear filters, includes an edge, then one of the gradients is going to be very large, right? If there is an edge and a corner, and the associated direction of the edge is going to be given by the partial derivatives here. Therefore, there's going to be an eigenvalue that is large, and all the other eigenvalues are going to be small, right, or 0. Now, so that's if there is an edge, but if there is a corner, then the two eigenvalues of this matrix, we should say there are only two. I said all, but there are only two, right? It's a 2 by 2 matrix. If the image includes a corner, what's going to happen to the two eigenvalues of that matrix? Where the two eigenvalues going to be? Very large, very good, right? They're both going to be large because you're going to have two edges in orthogonal directions. So both eigenvalues are going to be large. If there is an edge, one of them is going to be large, the other one a small or 0 if there's nothing. But if you have the two edges, then both are going to be large. And that's how you're going to know that you have a corner. For corners, the two let me call this h tilde because it's an approximation. The two eigenvalues of h tilde are large. Very good. OK. So the most basic corner detectors use that fact. A famous corner detector, famous in the sense of 𝗜ฐ์is a famous edge detector, if not the most famous edge detector. Maybe the most famous corner detector is called the Harris corner detector. And the Harris corner detector uses this idea of the eigenvalues. It computes the determinant of h tilde minus some constant alpha, the trace of h tilde. And remember that the trace of h tilde of any matrix can be computed as what? What's that? The sum of the eigenvalues. Very good. And I'm just going to divide this by 2 squared. This is it. With alpha, it's just a constant. With alpha some positive number. Okay. Okay. Now, Harris is just one of these possible corner detectors. If you look into the literature, it will happen as in 𝗜ฐ์, the edge detector, that you're going to find a large number of algorithms at variance of Harris using this matrix. There are others that use other criteria, but similar in spirit. Okay. Any questions about this? Now, corner detectors are a specific type of unions. Unions means that there's a union of two edges or more, right? In that case, a corner is defined by this type of union, right? But there are other types of unions that you might be interested in detecting. For example, classical things or detectors that you will see out there that are used all the time are T unions and K unions. And as the name indicates, a T union has two edges that look like this, right? And a K union has three edges that look like this, right? And as we did with the corner detector, you can just build a matrix that detects the orientation of these different edges, right? And study the spectral decomposition, for example, with eigenvectors, spectral decomposition of that matrix, and understand whether you have that type of units or not, right? Another way to do that, as you might see in the literature, is by using the word filters that we have already talked about. Okay. All right. That brings me to a very important topic that I'll keep mentioning, but I'm not going to talk a lot about it, or at least not very formally, which is space scale theory. And that goes back to work done in the 80s by mostly 𝗜ｈ𝘀𝘀𝗁 and Conjuring independently to define a set of algorithms to provide a large number of fiducial points, right, or points of interest from the image in low-level vision. Okay. What do I mean by this? Now, note that the edge detection that we have defined, as well as the corner detection, is always given at a specific scale, and that scale is given by the window, the size of the window of your filter, right? And that window is also given, if you use a Gaussian, by the sigma, right? The larger the sigma, the more of the image that you analyze or you include in that computation, right? The smaller the sigma, the smaller the window. Now, as I said today at the beginning of the lecture, what's an edge or what's a corner? Well, it depends on the scale that you're looking at, right? If I look at the tiny scale of an image of a face, any wrinkle on my face or any small hair is going to be an edge, right? Because any tiny variation in the grayscale value of the pixels is going to be considered a change. But if I look at a larger scale, right, I enlarge the image, right, I smooth it with a Gaussian, then only large changes across patches in that window are going to be considered edges, right? And in general, you do not know, and that's the key, you have no idea which scale is the correct one. So the idea of space scale theory is that you should actually compute everything from low scales or small scales, low values for sigma, to very high values for sigma, right? From very tiny image windows to very large windows. So you detect all the edges, but you detect them at different scales, and therefore you keep them separately. Okay? Now, here's where there are different models or different ideas or theories of what you can do with that space scale. Number one, which was the one that 𝗜h𝘀𝘀𝗁 actually pushed for, is that once you have, so imagine that, let me do that. Imagine that you start with an image, right? So that's your input image. I have that image that I have tilted like this, right? So we can actually look it from above, okay? And then what I'm going to do, I'm going to apply a first filter to that image, right? So this filter with, say, H1 with some filter, and that's going to give me this result, right? Or actually, why don't we say sigma 1, right? At the scale 1, right? Sigma 1. And then I'm going to do this for sigma 2, and that's going to give me another result at a larger scale, and so on, right? So from a smaller sigma, to larger sigma. Okay? And, whoops. And then what I'm trying to do here, right, this would be with h sigma max. Then what I'm trying to do is to find edges or unions that occur throughout my space scale, or at least in a large number of scales. And those ones that survive independently of the scale that I'm filtering at are really strong points of interest that I should keep. Okay? So that's theory number one. Okay. Theory number two is especially used, and we'll talk about a lot about this today, especially used to do matching between images. So imagine that you have two images, okay? So I'm going to have here my image one, and I'm going to do here image two, okay? So far, so good. And let's say that these two images have the same thing. Maybe there's a person here, maybe there is a tree here, right? What have you. And then the other one is taken from another vantage point. So the same person looks like this. And maybe, I don't know, there is some shelf in here, right, that we could see maybe here as well, right? And maybe you see a small portion of the tree and so on, right? And what's our task? Our task is to identify fiducial points from here and find the corresponding points there, right? This point here corresponds to this point there, and this point here corresponds to this point here, and this point here corresponds to this point there, and so on, right? Okay? Now, anyone can tell me a computer vision image processing problem where this is essential, and we need to solve this before we can actually resolve or solve that problem. One of the problems in computer vision image processing that we saw in 5460 that requires that pre-step. And actually, when we talk about this in 5460, I said, assume that you have these point correspondences, right? What area of computer vision is that? Or one of the main areas where this is required? Stereo, which is part of something larger, a more broader area, which we called, anyone remembers? What's that? What was that? A structure from motion is part of that as well. Yes, very good. Anyone remembers what that area is called? Multi-something. Multi-view geometry, right? Or of multiple images. And the idea in image processing and some computer vision is if I have multiple images, how am I either going to reconstruct the world in 3D, right? Using epipolar geometry, for example, right? We saw stereo vision, we saw structure from motion, very good. All these different methods that you can use to obtain or to get that result. Extraordinary. There's another thing that this could be used for in computer vision, which is for object recognition. And we'll get to that later on, right? Once we talk about high-level vision. And the reason is you may have a template. Let's say that this is my template, right? And my template may be that person without anything of these background objects, right? Or irrelevant object. And I want to find whether that template is included or represented in that image, right? And for that, the first thing, before I can do a matching, which we'll discuss later on in high-level vision, I have to find point correspondences where that matching might occur, right? That's going to be another application. So if this is your application, then that may not be the best model 2 or theory of space-scale theory to work with, but rather, you may want to look into the exact same thing, right? You extract your features at each of these scales. So that remains the same. You extract the features at each of these scales. And now you do this not only for image 1, right? But you also do this for image 2. And what would that look like? Well, now in that case, you're going to have a result image for the first scale, another result image for the second scale, up to the last scale, right? And I have all these results, correct? So far, so good? OK. And now, what I'm interested in finding a feature. Maybe I'm detecting, I don't know, K unions, T unions, corners, what have you. Here, with another feature somewhere else within that space scale model, right? And it might be in a different scale, because the object might be at a different scale in both images, right? So that is a way to try to find image point correspondences. OK? And now we're going to spend some time defining some methods to do that. And I'm going to define relatively modern methods that go beyond the classical space-scale theory of the 80s. These are methods that were defined in the 2000s that have their origins in a space-scale, but we have survived these two different basic ideas. All right, so let's see how we can do that. And as always, the two papers that I'm going to be describing here, or the main two papers, are also in Canvas, OK? All right, so let's look at local feature detection first. All right. So as always, we're going to start with an image I. So let I be the image of interest. OK. And we're going to consider W our window. OK. That window can be allowed to be of any size. Let's say n by n pixels. If you talk about pixels, sigma, if you consider a Gaussian window, right? There would be the variance of that Gaussian filter, and so on. And we're also going to, so this window can be at any scale, right? Sigma, and any orientation. Let's call it theta, right? So if I have my image here, my window could look maybe like this, right? Maybe like this. But it could also look like this, right? At a different scale and a different orientation, right? So I could say this is sigma 1, orientation 1. This would be 2, orientation 2. And sigma 3, orientation 3, right? And so on. Any orientation and any scale or size of that window. Now, what am I interested to? Remember, I'm here in model 2 or theory 2. I'm trying to find point correspondences between images, right? That's my ultimate goal. So this, it's going to typically be called invariance. And what it's mean by this, that we try to find points, right, that gives me the same image description. So when I compute the image description for that point, I get the exact same result independently of the scale, right, the size of the window, and the orientation of the window. So the result has to be invariant to scale and orientation. Okay. So to do that, I want to somehow normalize. The scale and orientation. Now, you can normalize it to any scale and to any orientation that you want, right? But for simplicity, I guess for us, for ourselves, we're going to consider that the normalized orientation is 0, right, at 0 degrees. And I'm going to consider, let's consider the center point first of the window as x0, y0, right? All right, so, and then we can just select a scale sigma 0 as our standard scale, right? So if I start here, right, I can write this as the set of all windows. So start with all these windows, right? And the first thing that I do is I normalize the orientation. So I'm going to get several of these windows of the same size, right, that correspond to either different locations or different orientations, right? And then of different size and so on, right, to the largest possible size. And then the final normalization is to normalize with regard to respect to the scale, where now I'm going to select a specific sigma, right, as the standard sigma, and therefore all these windows are going to be of the exact same size. I'm just going to resize all the windows to one standard size that I have selected. Okay? And let's say that this standard size right here is of n by n pixels. Okay, so far so good. That's easy enough, right? So you select a number of sizes, right? You have to select from which scale. Let's say, okay, let me do this. Why don't I say, I'm going to select from a minimum scale to a maximum scale, right? That's going to define the different scales I'm studying in my image, right? Obviously, my scale cannot be smaller than a pixel, but even a pixel doesn't make any sense, right? So I have to have a window size that makes some sense, right? Maybe 5 pixels, 6 pixels. It's debatable, but you can select whichever thing works for your application. You also need to select then the orientations, right? So say from min to max. I know if it makes a lot of sense to say from min to max, but you could consider 0 degrees as the minimum ren. You can go around, right, to 160 or 320 or whatever you decide that is relevant in your application, depending on how you compute the orientation of the windows to make sure there's no symmetries. Or if there are, and also the step, right? how many degrees from one to the other, right? So am I going to do theta 1 equals 0, theta 2 equals 1, meaning plus 1 steps, or am I going to do 0, 1 equals 0, 0, 2 equal 0.1, or 0, 2 equals 10, right? Well, it depends on what I'm trying to detect, right? Okay. Fantastic. And I'm going to have to use this throughout the image, as we always do in linear filters, obviously. Now, once I have selected this and I have extracted all my windows, right? I have computed the convolution of those windows with the image, and I have all my results. And I have normalized them, right? With respect to orientation here and the scale here. Now I have all the images of my image, right? Here, right? All that information in a normalized form, right? And then I'll repeat this here for my second image. So here I'm going to obtain, right? So this is going to give me a table, right? With all this, or a list, if you prefer, of all these different windows that I have extracted at different scales and orientations from image 1. And the same is going to happen here. I'm going to have all these window results, right? Okay. And now I need to find point correspondences, which means I need to write this in some space, right? Some type of a space. Let's call it maybe in the real domain, RP, that allows me to use a metric to determine which of these are close to this, right? Okay? So let's see how we can do this. So here's one way of doing this, of thinking about this. I'm going to define some properties of these windows, of these windows, by looking at the gradients of the pixels. Okay. So what I'm going to do for each of these windows, I'm going to look at the results of the pixels that I have in that window. And each of these locations is entries on that window. If I look at the gradient, for example, right, they're going to have a specific orientation, right? And so on, right? The gradient of these entries at the window are going to have a specific orientation, right? Right? That's what we have seen in our previous application of linear filters to detect edges, right? You compute the gradient, right, of the image, and you obtain these different orientations. The way I'm going to represent these gradients that we have computed before is using a histogram. So a histogram, remember, is going to give me on the y-axis the number or the percentage, right, of points in that window that correspond to, I'm going to say percentage, or you can say the number, same thing, that correspond to the x-axis. And here in this case, I'm going to consider the orientation of the gradient. And then maybe for this, I'm going to have a huge number or percentage of points in that window that correspond to 0 orientation of the gradient. Maybe very few that are at degree 1, maybe a little bit more at degree 2, and so on, right? And I'm going to end up with maybe something that looks like this. And this is a histogram that just represents the number of points in that window that have gradient at the specific orientations, right? I could compute other types of histograms. For example, instead of computing the percentage or number of different orientations of the gradient, I could consider as the x-axis the magnitude of the gradient, right? And that might be very different. It might look something like this. And so on, right? Okay. Now note that I can represent these histograms as vectors in RP, right? Because this one could be represented as an x vector. Let me call it z, not to be confused with x and y from the image, right? Could be z1 through zn square, right? If I had an image of n by n, I'm going to have this different types. I'm sorry, this is not n square. This is the number of orientations that I consider here. So the number of orientations, let's call it, q, my bad. And then z tilde, I'm going to consider the number of r, let's say, of different points of the magnitude, right? And I can represent these things as these feature vectors in my RP space, right? In a Hilbert space. And now I can use any metric to determine which points from that image correspond to which other points in that other image. You see that? By looking at similarities. Okay. Now, probably the most famous method that uses this idea is called Sift. So let's talk about this, a specific algorithm to do this. This is one of the most known methods of all of computer vision. And it's used all the time to find point correspondences in multiview geometry. Okay. And as I said earlier, you have the paper in Canvas, so please do take a look at that. So the idea behind Sift is that if we have an edge at multiple scales, as I have defined in the space scale theory, right? Then that's a good edge. If the edge is present at multiple, then, or let's just say then, we consider this a good edge. To do that, we can use the Laplacian of Gaussians. In Sift, usually you're going to use the second order derivative. Right? Therefore, the Laplacian. And remember that we have talked about this earlier, that in 1D, that would correspond to the so-called Mexican hat that looks something like this, right? Which is the derivative of the Gaussian with respect to your parameters. Let's do it like this. Now, it is worth mentioning that to use the Laplacian, the second order derivatives, you may want to actually estimate this as a difference of Gaussians. And that's a really good approximation to use. So what you're going to do is you're going to take a Gaussian at the location x, y for some scale k times sigma minus the Gaussian at the scale sigma, and you want to normalize this by k sigma minus sigma, right? Yeah. And the reason this happens is if we look at this again, right? If I take this Gaussian and I subtract another Gaussian, right? Or subtract this from the other, then, right? If I do that subtraction of this minus this, what I'm going to obtain is this, right? So this is a good approximation that just computationally is very efficient because it's a simple subtraction of Gaussians. So you'll see that Sift actually generally uses that trick as well. And you can do that for, so for example, you can do that at sigma, then some constant times that sigma. You can do maybe that constant squared times sigma, and so on, right? Maybe cube times sigma, and so on. Okay. Now, how you build the specific algorithm doesn't have as nice as a theory as I have defined earlier for a space scale. But people do this because it just works. And we will talk a lot about this in computer vision. There are things that just work, right? And gives us good results with the images we typically work with. Okay, so let's get into some of the details of the algorithm then. One thing that the algorithm does is to detect peaks. You can call it peak detection. So I'm going to compare, to detect a peak, a local peak of the detector, I'm going to compare the detection at each pixel in my image with its neighbors. Okay? I'm going to use some random number of neighbors. In Sift, usually you do a comparison of the results at each location with its 26 closest neighbors. And from that, you're going to detect the peaks, meaning you're going to select the minimum and the maximums, right? At each pixel. Another thing that is conveniently done in Sift is to delete detections in low contrast areas. Why would I do that? Because if I have a really low contrast area, there is most likely not an edge. And if there's no edge, then in the basic classical model of computer vision that we are using, there is no interest, or there's nothing, no fiducial point of interest for us to detect. Okay? Another thing that you will see is that you can previously specify maximum and maybe minimum values for the peaks that we have detected here in step 1. And the reason for this, and these values for this maximum and minimum are taken from experience. And you'll see in the Sift implementations that are out there that people have already given you the actual numbers. This is to detect outliers, because you're always going to have noise in the image that's going to give you outlier detections of peaks in many locations, right? So this is just, I put this in parentheses, this is just a step to eliminate some of these spur detections that we talk about when we talk about canny edge detection as well. You could also use the idea of the Harris corner detector to eliminate outliers, right? So, for example, remove detection where the values, so remove the detection of points with values that have, say, a trace of, remember that H tilde that I mentioned over the determinant of tilde, H tilde, excuse me, right? Where that value is larger than the specific threshold, right? So, for example, in the classical Sift paper that you'll see online, remember H tilde is defined as the derivative of xx, xy, yx, and yy, right? This subscript specify the partial derivative with respect to each of the 2 dimensions. So that's the same matrix. And you know that the trace of H is equal, as we said earlier, to the sum of the 2 eigenvalues, lambda 1 and lambda 2. And the determinant of H is going to be equal to, anyone knows? The product of the eigenvalues, right? Lambda 1 and lambda 2. And therefore, you could write that this is equal to r plus 1 squared divided by r, where r is equal to lambda 1 over lambda 2. Okay? And in Sift, you eliminate points, or fiducial points, I should say, with r larger than 10. Okay? So, you could have changed all this with a simple edge detector, right? You could have used the first derivative of the Gaussian to detect edges, and all the points in the edges would be your points of interest. You could do that at 1 scale, at 2 scales, at 10 scales, at as many scales as you want. You could do, instead of edges, corners. You could do other types of unions at different scales, at different orientations, and so on, right? Sift instead uses that different approach where you detect first the peaks, and then you start eliminating things that might be spurious to your task, okay, or to your detection. Same thing, just another way of finding points of high relevance in the image that then you can use that descriptor at the very end of the board, right, that we have discussed before, to represent the values or the relevance or the information, if you will, of each of these fiducial points that I have extracted. And then that representation is what allows you to do matching across images. Now, the reason people prefer to use Sift instead of using edge detection or union detection is because this algorithm is very efficient and works really well in practice. That's it. That's the only reason. But it became absolutely a must-have tool in your arsenal if you want to do computer vision. Okay? And we're going to work on this in our homework, obviously. I'm going to post first homework sometime this week. Not today, but sometime this week. Don't panic. Not yet. Maybe tomorrow. Most likely not. I guess Thursday or... Okay. How are we doing on time? Okay. The last thing that I want to talk about, I'm just going to summarize it now today, and then I'm going to give you the more formal description of this in the next lecture. The other thing that I want to do is to do all of this as fast as I can. Because although this is an efficient algorithm that works really well, it's not as fast as we may want it to be, right? Because if I have just two images to match, that's a simple task. But for example, in object recognition, when we get to high-level vision in object recognition, and we have templates, let's say maybe just one template for each object, or maybe 100 templates for each object, and we want to find whether, I don't know, 1 million different objects that I have. So if I have 100 samples of each object, I have 100 million templates. And I want to match this on a number of images that I have, right? Maybe 1,000 images, right? And I want to do this to identify which objects I have in each of these images. Then I'm talking about 100 billion different matching that I have to do. And the faster I can do each of these matchings, the better, right? So these things are extremely important that we can do them very fast. If I do multi-view geometry, right, in computer vision, then what I need to do, if I have very long sequences of images, right, either a lot of cameras in multi-view geometry for stereo, for example, or if I do structure from motion or other methods, I want to have as an algorithm that works as fast as possible so that then I still have computational power or time to compute the reconstruction of the 3D structure quickly and efficiently, right? And that means I need an algorithm to do this very quickly. And there's an extension of Sift called SURF, which actually uses a very famous technique in computer graphics and in math that allows you to do these multiplications and these computations extremely fast. Paper also in Canvas. So look at these two papers tonight and tomorrow. And then on Thursday, when we look at this, you'll better understand the tricks that I'm going to use to make this go really fast. All right, I'll see you then.